Okay, so now we will start a new topic. This is product spaces. So let us take x s mu and y t lambda measure spaces. So we want to define a sigma algebra and a measure on x cross y which is compatible with the structures on x and y, and also we want to relate the process of integration on x cross y with the process of integration on x and on y. So our first aim, of course, is to come study the sigma algebra which is there, and so we will do that to start with. Then we will have to look at measurable functions and then finally integration. Okay, so definition. A measurable rectangle is a subset of x cross y of the form A cross B, A in S, B in T. An elementary set is a finite disjoint union of measurable rectangles. The sigma algebra generated by elementary sets is denoted S cross T. So S cross T is a sigma algebra on x cross y, and it is generated by the elementary sets. The elementary sets is the finite disjoint unions of measurable rectangles, which are just products of sets taken from the two individual sigma algebras. Next definition: xy non-empty. Of course, they are always non-empty, so we don't have to say this again. E contained in x cross y and x in x. Then we say the x section of E and say y in y, denoted E sub x is the set of all y in y such that xy belongs to E. So this is a subset of y, remember. Similarly, the y section of E denoted E sub y, super y, is set of all x in x such that xy belongs to. And this, of course, is contained in x. So proposition. So this is a test for measurability. So xs yt measurable spaces. E contained in E belongs to S cross T, the sigma algebra. Then for every x in x, for every y in y, we have Ex belongs to T and Ey belongs to S. So this is a test of measurability. If this does not happen, suppose you have a set E whose X section does not belong to T for some X, or for a Y section does not belong to S for some Y, then the set is not measurable, because if it is in S cross T, both of these must happen. So this is just a test of measurability. So proof. So let U equals be the collection of all subsets E in X cross Y such that E sub X belongs to T for every X in X. So now we want to see what kind of set this U is. So if you have A cross B, E equals A cross B measurable rectangle, then what is E sub X? E sub X is equal to B if X belongs to A, and will be the empty set if X is not in A. Because E is A cross B, if X is not in A, then for no Y, XY will be in this thing. Similarly, if X is in A, then all of Y, any Y in B will be in E, and therefore you have EX is this, and therefore this of course belongs to T. Therefore any measurable rectangle belongs to you. Okay. Now in particular X cross Y itself belongs to you. Okay. Now if E is contained in X cross Y and X is in X, then what is E sub X complement? This set of all Y in Y such that XY is not in E. Y is not in EX, that means XY is not in E. And this is nothing but E complement X. So if E belongs to U, then E sub X will belong to T, implies E sub X complement will belong to T, implies E complement X belongs to T, and therefore this implies that E complement belongs to U. Similarly, if E equals union I in I, EI of EI with EI in U, okay, then E sub X is nothing but union I in I, EX, EIX, and all this will belong to T because each of them is in U, and therefore you have that E belongs to U. Therefore U is closed under countable unions and complementation. It contains X cross Y, therefore U is a sigma algebra containing measurable rectangles. If it's a sigma algebra containing measurable rectangles, it's going to contain all the elementary sets, implies U is a sigma algebra containing elementary sets, and so U contains S cross T. So every element in S cross T is in U, that means E sub X is in T. Similarly, so this implies for every E in S cross T, for every X in X, you have E sub X belongs to T. So similarly, we can show for every E in S cross T, for every Y in Y, you have E sub Y belongs to S. So that completes the proof of that thing. So now we have seen rings, we have seen algebras, we have seen sigma algebra and so on. Now we are going to define one more collection of subsets of a given set X. So X is a non-empty set. A monotone class M of subsets of X is a collection of subsets of X closed under increasing unions and decreasing intersections. What does that mean? That is, AI contained in AI plus 1 for all I, BI contains BI plus 1 for all I, AI, BI in M for all I implies union AI, I equals 1 to infinity belongs to M, and intersection I equals 1 to infinity BI belongs to M. Increasing countable, closed and increasing countable unions and decreasing countable intersections. So such a set is called a monotone class. So remark, trivially, Px is a monotone class. Any sigma algebra or sigma ring is a monotone class. So if A is a collection of subsets of X, then Px is a monotone class which contains A. Okay. Now intersection of monotone classes is a monotone class. That's easy to see. Therefore, there exists the smallest monotone class containing A, and this is called M of A, and this is also called monotone class generated by A. So given any collection, you also have this. Okay. So now lemma. X non-empty set and M monotone class on X. Let P be contained in X. Define U of P equals set of all Q contained in X. So set P union Q, P minus Q, Q minus P belong to M. Then UP is a monotone class. So proof. So let us take Qi I equals 1 to infinity, increasing sequence in UP. Then P union Qi, I equals 1 to infinity is increasing in M, and P minus Qi minus P, I equals 1 to infinity is also increasing and in M. And since M is a monotone class, this implies P union Qi, I equals 1 to infinity, which is union P union Qi, I equals 1 to infinity, belongs to M. And similarly, union Qi, I equals 1 to infinity, minus P is equal to union I equals 1 to infinity, Qi minus P, and this is increasing, and therefore this again in M. Now, P minus Qi is decreasing in M. And P minus union Qi, I equals 1 to infinity, is nothing but intersection P minus Qi, I equals 1 to infinity, and this is a decreasing thing, and therefore this also belongs to M. So this implies that union Qi belongs to UP. Similarly, if Qi is decreasing in UP, then intersection I equals 1 to infinity of Qi is also in UP. Therefore, UP is a monotone class. Same type of proof, elementary set theoretic arguments. Next lemma. This is an important one. So this says if X is a non-empty set and R an algebra of subsets of X, then M of R, this is nothing but the smallest monotone class containing of R, is equal to S of R, the smallest sigma ring containing of R. So monotone class and the sigma ring generated by an algebra are one and the same. They are not two different objects. Okay. Proof. Let P belong to R. Now if Q belongs to R, then P union Q, P minus Q, Q minus P all belong to R, because R is an algebra. And this implies that P union Q, P minus Q, Q minus P all belong to M of R, because if they belong to R, they belong to M of R, because M of R is bigger. And therefore, this means that U of P, this means R is contained in U of P. Because for every Q in R, these three have, and R is contained in U of P. And if U of P is defined as in the previous lemma, defined with respect to MR as in the previous lemma. MR is a monotone class, so we can define like this. So R is in U of P, R is And since UP is a monotone class, containing R implies UP contains MR, because MR is the smallest monotone class. So now let Q belong to M of R. Then if P is in R, then we just saw Q belongs to UP, because M of R is contained in UP and therefore Q belongs to UP. And by symmetry, you have P belongs to UQ. So this implies that R is contained in UQ, and this is a monotone class. This implies MR is contained in UQ. So if you have for all P and Q in M of R, MR is contained in UQ. This implies that P union Q, P minus Q, Q minus P belong to M of R. That is, M of R is an algebra. Now, EI, I equals 1 to infinity, countable collection in MR. Then Fi equals union, Fn equals union I equals 1 to n, Ei belongs to MR, because this is an algebra, and Fn is increasing. This implies union I equals 1 to infinity Ei equals union I equals 1 to infinity n equals 1 to infinity Fn belongs to MR. So this implies that MR is a sigma algebra. Okay, and it contains R, and therefore you have MR contains S of R. On the other hand, SR is a sigma algebra, is a monotone class. And this implies that SR contains MR. So MR is contained in SR, SR is contained in MR, and therefore this implies that SR equals MR. So if you have an algebra, then whether you make the monotone class or as sigma algebra, it doesn't matter. Okay, so next proposition. XS, YT measurable spaces, then S cross T is M of E, where E equals elementary sets. So if you take all the elementary sets, then the sigma algebra generated by elementary sets and sigma algebra and the monotone class generated by the elementary sets, both are one and the same. Okay, so proof by previous proposition, enough to show E is an algebra. So of course X cross Y is a measurable rectangle, so trivially it belongs to E. and you have A1 AI in S, I equals 1 2, BI in T, I equals 1 2, then you must, this is just some set theory which you should check. A1 cross B1 intersection A2 cross B2 is nothing but A1 intersection A2 cross B1 intersection B2, and A1 cross B1 minus A2 cross B2, this is equal to A1 minus A2 cross B1 union A1 intersection A2 cross B1 minus B2. Okay, this is check. Okay, and therefore intersection of measurable rectangles is a measurable rectangle, and the difference of measurable rectangles is the disjoint union of measurable rectangles, therefore is an elementary set. Therefore you have that, so this implies, so if you take any elementary sets, then the different union and difference will just be again an elementary set because of these two relationships which we have used, and therefore E is an algebra. What is E? E equals finite disjoint unions of measurable rectangles. Okay, and therefore that is again an algebra, and then by the previous theorem we know that the sigma algebra generated by this and the monotone class generated by this are one and the same. So we will continue with this next time.